And then you can decide which one you want to use to solve a problem. So I'm going to go over this one, SSPH. So as we said in the morning, we have particles on this domain. And as you can see, we are not numbering elements. So these particles, there is no connectivity between the particles required. So we want to find f, we want to find a function, the value of the function at this point where I put x in terms of the values of the function at these particles or nodes or points. So now we know Taylor series expansion. So the Taylor series expansion says that f at a point equals f in the neighborhood of that point. So I'm expanding f in terms of values in terms of Taylor series around this point where I am interested. So this is the point xint plus derivatives that point times zeta minus x interval plus second derivative at this point times zeta minus x int square. And so this is our approximation. We are not going beyond the, if you like, you can go up to like next term, or it's up to you. You can keep as many terms as you wish. So what this will do is, this will say we have 1 zeta minus x and zeta minus x square. So it's a quadratic complete polynomial of degree 2 because you have 1 zeta square. And what we are interested in is finding f prime and f double prime. So we want to find the values of this function f. F can be same as u. U was the displacement we were talking about in the morning, so f is u. If you have a two-dimensional problem, then f can be u1, u2, like displacement in the x direction, displacement in the y direction. So let's call this one, say, t, and this is a function of zeta, which is really a function of zeta minus this, but it's easy to write only function of zeta. Oh, 1 over 2. Let's say 1 over 2 here. And then this is a function of q. And thus, so our goal is to find this in terms of the values of f at these particles. So procedure is similar to what we did in the morning. Actually, it's a little bit maybe simpler. So we take a weight function like we did there. So you take a weight function around that point. similar to what we have there. So we multiply by the weight function. XINT is fixed, so I did not write it. But if you want, I can put W of that. Also, oh, sorry, I should put index here too, because this is P alpha, Q alpha. It's summed on alpha. Alpha goes from like 1, 2, and 3. So let's multiply by P beta also. And W. Is it okay? I mean, nothing, we have not lost anything. We have multiplied by P on both sides, multiplied by W on both sides. What is our goal? Our goal is to find this, Q. So now since we have not brought in the information yet here, so we sum this, we evaluate this over we evaluate this both sides at each one of these points, which are wherever W is non-zero, they will contribute. You can say we evaluate it everywhere, but it's up to you. So whatever is in the, English speaking, in the compact sort of this function, wherever this function is non-zero, we will get a contribution. So now we have summed down J. So J goes from 1, 2, 3, 4, 5, but G of J equals, G of 1 equals 1, sorry 2, G of 2 equals 3, G of 3 equals 4, and so on. So G is the global numbering, J is the local numbering. Because we need to keep track of which particles we are summing on. So G is the global numbering, J is the local numbering. Does that make sense? We are done. We are basically done. On the left hand side, this is the value, or supposedly this is the value of the function at the particle Gj. This is all of this will be summed. Q is not summed. Q is XINT. So that is where we are interested in finding the function f and its value and the derivative of its value and so on. The rest, everything can be evaluated. Once you choose the weight function, this is a polynomial, like here zeta minus xint, zeta x minus int squared. So once you know which point you are interested in, this you are choosing now 2, 3, 4, 5. In this picture is 2, 3, 4, 5, 6. right? So I can solve for Q. So Q equals whatever this thing is, say A alpha beta, and this thing, there is an F in it, so I need to write, okay, what I'm going to do is say this is A alpha beta inverse, and that term, and that has F in it. And with sum, and this is summed on J. All I'm doing is pre-multiplying by A inverse. Oh, there's a W also, yeah. This is not F, it's W. So it's W, O, F, P. Right? W, F, P. W, F, P. Is it okay or not? Akshay, speak up, it's okay, you can ask. I'm sorry? Oh, here. There will work probably, you never know. Try it. Huh? They're working? Good. You can use it, but I will need it after I leave the class. Okay, so we can call something this one. So for alpha equal to 1, you will get alpha equal to 1. This is summed on beta because beta is a repeated index, and then it is summed on j here. But so what you will get is in terms of the values of f. So this one is really makes life very simple because this one tells you that the value of the function, that the approximate value of the function at this point, even though we, in our case, the only approximate, well, not only, one approximation we have is we cut off the Taylor series. We truncate the Taylor series. Right? So what we have done is we have expressed f in terms of some quantity here. This was g of j. And there are something here that depends upon j. Because this thing is summed on j, right? If you take alpha equal to 1, you get this term. You get the function. Because what we did, we solved for q. This matrix equals that. Pre-multiply by A inverse, you will get q. And then you do some, not manipulation, but you rewrite it so that you have Q here, you have some matrix here, and this F here. So these are 3 entries here. So this is 3 by 1. And this depends upon the number of particles which are in the domain of influence or contact port of W. So if there are, say, 6, in this case we have 1, 2, 3, 4, 5 particles I drew there. So that means this one is 5 by 1. So this should be here 3 by 5. And so this one has, there are 5 of these, there are 5 of these, so you are summing them, so you get a scale. And if you want the derivative, then you can again get J, but now you have a different function, and F of zeta G of J. So you have a different function here, and same thing if you get the next one, second derivative. So that's the third function. So say psi hat G of J, F of zeta G of J. And now we are in good shape. So we got function, we got its derivative, and you got its second derivative, if you like. So this one has a better accuracy than this one has a better accuracy than that, because we truncated the Taylor series. No, this is a different function, because you are picking up different row of this. You are picking up the third row. Here you are picking up the second row, alpha equal to 2. Here you are picking the first row, alpha equal to 1. So these 3 functions are different. This one is same. And again, there is no, actually, these values you will get of F, they are not the values of the function at the particles. They are fictitious values. The rest of the work is same as we did in the morning. If you like, in this case, you don't need to derive the weak formulation. Our equation is rho delta square u over delta t square, and let's say we have a isotropic linear elastic material. I don't have the nonlinear part. So I can, my u is F. U is F, right? So I can write this as rho summation on J psi of G J F. No, it will be F double dot zeta of G J equals E sum on J psi hat of, no, not psi hat, but this one will be psi tilde, this G of J, and F of zeta G of J. So I can work with the strong formulation of the problem. I'm working with the given differential equation. We have not derived the weak formulation. We can derive the weak formulation too, so it's okay. But you can do both ways. You can do, if you will use weak formulation, then you will need U prime. So you use this one on the right hand side. And if you are using strong formulation, then you have U double prime, so that's this one. So when we say strong and weak, it is in terms of the derivative. It's not in terms of the strength of the person. So again, we have to impose the displacement type boundary condition separately. So we write this This you can think of being a collocation method. This you can think of being a collocation method, because what we are going to do is, if we have 8 particles here, so we need 8 equations. So we are going to choose points, say 8 points. I call them xi and t, but I can call them collocation points. So if we have 8 particles, we need 8 equations. So you choose 8 collocation points and satisfy your differential equation at those collocation points. It's a meshless method. There is no connectivity required. And the 8th equation, we will need to impose the boundary condition. So if you are given that the displacement at the 8th node is 0 or 5, whatever value you are given, then you take this and use that to impose the displacement type boundary condition. If you make your W as a direct delta function in the weak formulation of the problem, then yes. Not here. No. Because if you make your W as direct delta function, then there is no connectivity, there is no information being transferred from anywhere. So if you call it a collocation method, then yes, you can see it's a special case of Petrov-Gherkin formulation, in which the test function is a direct delta function. So this one looks simpler than what we did in the morning, like moving least square approximation. To me, it's not, and incidentally, this is due to the paper you will get has 2 names, Zhang and I. Zhang is this his thought process, his idea. GM Zhang, he was a postdoc from mainland China. And I've been very fortunate to have people from mainland China. Many of them have come with their own money, or money from the Chinese government. But for him, no, I supported him. But many have come with the Chinese government money. So all we have to do is find F. Done. Again, after you find F, you still, if you want to find a solution here, you still have to go back to this process. These are not the values of the function at the particles. These are fictitious values. So you have to go through this process again. So, any questions you have? So it's your choice now. You can do the problem that we were doing on Friday, that wave propagation in a bar, either by using SSPX basis function or moving least square approximation basis functions. And Zhang, he solved wave propagation problem in a functionally graded material with both basis functions. So he used a different one, which I have not talked here. That's called MSPH, modified smooth particle hydrodynamics method. But this one is simpler than either this SPH, like smooth particle hydrodynamics method, and it is simpler than the MSPH, modified smooth particle hydrodynamics method, and is probably simpler than RKPM. However, RKPM has one advantage, which this one does not have. RKPM, this is due to people at Northwestern. This one does, if you use this has the property that it equals 1 at a given particle and 0 at the remaining particles. We construct these to satisfy that condition. And then these values you get F here, they are the values they are the exact values at the nodes, like in the finite element method. But other methods do not satisfy that condition. So the ball is in your court, and whether you use this or you use, unless you struggle with it, it's not easy to learn. If you ask me to repeat, I can repeat 10 times, but it's the same thing. So you decide which one you want to use, and you need to write that software, and maybe if you don't want to use 10, you can use 5. 10 is a reasonable number in a way. Because you need some connectivity for the waves to propagate. And the connectivity is coming through that weight function. It's coming through this. So either you can use Gaussian, like e to the power minus something, or you can use polynomial. The results will be different in the two cases. So eventually if you use a lot of particles, the results will be the same. But if you are using 10 particles, then the results from the two weight function will be different. Also the results from how much, what should be the h, like on what length should they be non-zero, results will depend upon that. And as we discussed in the morning, there is no guarantee that the mass matrix you will get, the sum of all elements will equal the mass of the structure. Okay, so I'm done. It's your job. Now I will be here, of course, but you try to write. Unless you try to write and make mistakes, it's not going to be easy. And it's unfortunate that I did not write, so I don't know what mistakes one commonly makes. And I can tell you what mistakes one commonly makes in the finite element codes, but not here. And that too I did. I think the last time I wrote a code was probably 1988 or 1990. So that was the last time I wrote a code from scratch. Okay. Good luck.
Speaking.
Well, the wave propagation problems you are studying, the units we are taking should be selected carefully. So the unit of length, should be either millimeter or micrometer, not meters. The unit of mass should be either gram or milligram. Units of time should be microseconds, and then based on these, find the unit of force. And you will see that the value of E you have it given in the problem. That's like 200 times 10 to the power 9, or 2 times pascals, 2 times 10 to the power 11. In these units, that value will be something like maybe 200 or 20. So see, going from 2 times 10 to the 11 to basically 20, nothing will change. Your answer will be still, your answer will come out to be, when you get the answer, it will be in terms of millimeters, gram as unit of mass, and microsecond as unit of time. So now if you are taking a time step size of the 10 to the minus 11 or 10 to the minus 10, then you will be taking maybe 10 to the minus 1. And if you recall, we have in one of the formulations k plus 1 over beta delta t square m. So this, when you are dividing by delta t square, and delta t is of the order of 10 to the minus 10 or 11, this term will become 10 to the 22. So it can cause truncation errors. I'm not saying it will make your answer wrong, but it can cause truncation errors. If you multiply, then this term will be 10 to the minus 22 times k. Again, same issue. Unfortunately, these days, the word length in the computer is 64 bits or bytes. So it's manageable. But it's better if you use these. If you read the LS Dyna user's guide, that's what it tells you, that you should take these as the units, not meters and kilograms and seconds. That is just to avoid getting large numbers. Okay, yeah, now we can talk. I think if you go to you can check, I don't know if you have access to the internet here or not, but if you go to this website, there is a software, there is a code for MLPG. Source code in Fortran for MLPG. I think it's to study dynamic problems. Yeah, I think that code was developed by Ching, C-H-I-N-G. It gives you the common cause. So you are welcome to borrow it, download it, not borrow it. You are welcome to download it, do whatever you will, you use with it. If you use it, please acknowledge that you borrowed the code from this website. And then you can modify it to suit your purpose. We are not responsible for any errors. Okay, so don't. I think this code is fine. It does not have any issues. But I need to say that. Otherwise, if something is wrong and then supposing you are doing PhD and you use that code and something is wrong and then you will say, oh, my PhD is delayed by 1 year because you told me I can use that code. You are welcome to download it, but you are responsible for making sure that the problem you are doing, this code can do it and you are getting correct solution. And if I get time, I will put in, I will upload a code for transient elastodynamic for thermoviscoplastic materials. So then you can do couple thermal, elastic, as well as plastic problems. And it will account for strain rate, strain hardening, strain rate hardening, thermal softening. The only issue is it does not do any contact problems. But otherwise, yeah, it can solve those other problems reasonably well. Fortran, because that's the only language I know, and that's the only language in which my students develop the code. Some of them develop in MATLAB because they don't listen, and then sooner or later they find out they cannot do a real size problem. One student knows she is developing in C++ because when she came, she was a computer science major. So she's developing in C++. But I do not know. The Fortran, at least I understand. Basic one can understand. Mathematica, you can figure out what is going on, even if I don't know the commands. But C++, I have no idea what it is. So whenever there is no guarantee that it will be done next week. No. That code has been with me for 2 years and I have not uploaded yet. So I don't know when I will upload it. But I do have it. So, okay. Thank you.
Yes, some students have.